Greetings. Welcome to this discussion on non-Newtonian fluid flow in slits. So let us recollect the way we have discussed flow of Newtonian fluid through slits and the flow we encounter in case of plate heat exchangers. So what happens is that gap between two plates is quite small. Wherever this particular width is quite large. Okay, and fluid is flowing through this gap from left to right. So this is one plate and this is another plate. One plate is being placed above another with some spacing provision for maintaining the spacing or some spacer. And in case of plate heat exchanger, you know that gaskets are used. Okay, so with some support, that gap is maintained. Then fluid is made to flow from left to right because of pressure. Okay, then so what happens is that the gap is quite small as compared to, or you can see in this particular case we can say that in z direction distance between the two plates is quite small as compared to the width of the plate, which is actually we are saying that W means quite large width in y direction, and flow is happening however in x direction. Okay, so now for this analysis what we are saying that let us consider not the whole layer of fluid but a very small layer of the fluid whose thickness is actually delta z, but its width is remaining W again and it is moving in x direction. Therefore actually while considering this particular strip, you will have to recognize that this flow pattern will be symmetric with respect to the central plane. You see, at the center the velocity will be maximum. Towards the top and towards the bottom that velocity is decreasing, and at the interface with the top plate and bottom plate the velocity is becoming 0. So the midpoint is of concern actually. See this, there is a axis passing through the midpoint and this central plane. So fluid moving at the central plane will be moving at the maximum speed. So now starting from the central plane above, whatever we are showing on the right hand side, that starting from the central plane, whatever is fluid layer is there above it. So for that layer let us consider a layer of thickness delta z, so that is a bottom side's coordinate z coordinate is z and top side's z coordinate is z plus delta z, and width remaining same W. Okay, now for that layer of fluid let us consider thickness of delta x. From the left hand side some position, so this is the position x, so therefore this position here will be x plus delta x, and this height is delta z. Okay, and you see we are showing that it starts from z is equal to 0. So whatever is happening at the top, similar means incident we will be seeing at the bottom side also, and that will be symmetric to it, so we are not considering in our discussion. So whatever happens above 0 will be just replicating it in the same way for the fluids falling below the central line. Okay, so now net positive forces acting in positive x direction here will be near to the maximum velocity. So here maximum velocity occurs at location z is equal to 0. So positive z direction here will be the higher positive, you can call it positive shear stress will be acting in this direction, and at location z plus delta z it will be acting in the opposite direction, because you see we are expecting that velocity profile will be like this. Yes, near the center it will be higher and near the top surface it will be 0. Okay, therefore actually see what will be saying, the positive directional forces, that this particular value minus this one, this is in negative direction, multiplied by the this length multiplied by the width across this plane, so that is W. delta x into W. Now what is causing the fluid to flow is actual pressure. From the left hand side there is Px, and from the right hand side P at position x plus delta x. So now Px is supposed to be greater, then only actually the fluid will be moving from left to right. So at Px, we are talking about this is a positive forces, so Px minus Px plus delta x. The whole thing should be multiplied by this particular, you see, this particular distance, that is delta z into W. So this pressure force is acting on this particular height and depth of W across this plane. Okay, so now both the sides you divide by a factor called delta x into delta z into W, then you are going to get this particular expression. So then you get this particular expression, or del of tau zx del z is equal to minus delta p by del p del x. Okay, now this is the, you see, what you call is the hydraulic gradient or pressure gradient causing the fluid to flow. So this same thing actually we sum it up as a delta p by L. Now this expression, so we are just simplifying it for, because they are constant terms, delta p by L we are writing as a delta p by L. So now we can integrate by separating the variables. Then we get tau zx is equal to delta p by L into z plus a. Again, you see, this is constant of integration. So now boundary condition is applied. Tau zx is equal to 0 at z is equal to 0 leads to a is equal to 0. It means tau zx is equal to delta p by L multiplied by z. Okay, z means position. Its position starts, you will have to measure that position with respect to the midpoint of this particular gap. Okay, so there is a central plane. From the central plane we will be moving upward. That is it. So what we have seen, that the shear stress is pressure gradient and z. Z is the location with respect to the central axis. Now for non-Newtonian fluid, or specifically that fluids which are following this power law equation, so we are writing the expression for tau or shear stress in this format. Okay, K into shear rate to the power n is equal to delta p L into z, delta p by L into z. Okay, so then we do this manipulation as we do for non-Newtonian fluids. 1 by n is the power now on the right hand side, z. So by integration we get this particular expression. So this is the integration step and this is actually the solution step, and then we get this constant of integration. So this task here will be to eliminate this constant of integration. Boundary condition, we know that at the central axis the velocity is maximum, and on the other side velocity is 0 when the fluid is touching the solid plate or solid surface. Okay, so that is the starting from the central axis up to the half thickness or half depth of the slit. Okay, so then we get the value for this constant of integration. So on substitution of this value for constant of integration, we can compare actually this, what is the value for constant of integration. So this factor remains same, this factor remains same. Okay, only thing is that z is getting replaced by this delta, half thickness. So now means actually when we substitute value for a, so this factor will remain as such. Only thing is that in one case it is delta to the power n plus 1 by n, and another case it is z to the power n plus 1 by n. So now when we simplify it, we get up to this, it is the expression for a, then 1 minus this z by delta to the power n plus 1 by n. So z by delta is the, you can call it relative position. Okay, so maximum value can be delta and minimum value can be 0. So in between this z value will be varying. Okay, now velocity is maximum at central axis location. Okay, means when z is equal to 0, velocity is maximum. Therefore, when we substitute z is equal to 0 in this expression, we get this maximum velocity. So maximum velocity is again this particular factor. So now we can compare, actually maximum velocity is this value for a, a means constant of integration. Okay, so maximum velocity is this particular expression. Then we can write this expression for Vx at location z as a equal to V maximum multiplied by 1 minus this relative position, that factor relative position, to the power n plus 1 by n. So this is actually quite easy to remember. So V max into 1 minus relative position to the power n plus 1 by n. So this is a kind of, let us say, constant which is independent of the position. Okay, only this part is a function of position. So then from the definition of average velocity, this that already actually shown in the earlier case of Newtonian fluid flow as well. So we are talking about this half of the slit only, upper part of the slit from 0 up to delta. So then this, you see, this flow area is basically delta and w. Okay, so then velocity into w is the width of the slit, just like the same w, and then this we are integrating in z direction. Okay, so Vmax by delta, then this particular factor is Vmax, it is independent of position, so it can be taken out. So only dependent part will be this one minus relative position. So we are integrating it from 0 to delta. Now transforming the variable, so relative position we are defining as y. So then we can get this expression for z and delta z. Also the limit changes now from, earlier if the limit was from 0 to delta, so now it will be becoming from 0 if z is equal to 0, y is equal to 0, and if z is equal to delta, then this factor is 1, so 0 to 1. Therefore V average is equal to V maximum by delta 0 to 1, 1 minus y to the power n plus 1 by n, and this delta into dy. Okay, so then what we get, these deltas are getting cancelled, so V maximum into y minus n by 2 plus 1, 2 plus n, sorry, 2 twice n plus 1 to the power y to the power twice n plus 1 by n, 0 to 1, and then we get this expression. So this is the first task of obtaining an expression for average velocity. Okay, so we'll continue with the remaining discussion.